Hey, Math 1030, Mrs. Bricky here, and this is Lesson 8B. We're going to be talking about doubling time and half-life. So exponential growth leads to repeated doublings, like with the penny. It doubled to 2 pennies, then it doubled to 4 pennies, then it doubled to 8 pennies. And exponential decay leads to repeated halvesing. That's the amount is being cut in half over and over again. So we're going to be focusing today on doubling time and half-life, or the amount of time it takes to cut the amount in half today. All right, so first doubling time. The time required for each doubling in exponential growth is called the doubling time. And this is denoted as a capital T with a subscript of double. So it's written like this. After time t, you can figure out the growth factor by calculating 2 to the power, the amount of time divided by the doubling time. So that is like a fraction power. Um, And then if you want to calculate the new amount or the new value of whatever is growing, you can use this equation. The new value is equal to the initial value multiplied by that growth factor. So just one word of caution on this is that the time units must be the same between the two times. So if your doubling time is in months, you have to use the given time in months as well, or if it's in hours, they both need to be in hours. So you may have to do a little bit of time conversions with this. So I'm going to do some examples, and then I would suggest after I do these first, I think, 2 examples, that you open up the homework, pause the video, and then go and do number 1, 2, 5, 6, 7, and 8 on the homework, and then come back to the video and watch the rest of it, and I'll kind of tell you along the way which homework questions go with which parts of the videos on this one to kind of make it easier for you. So here's our first example. The doubling time of a bank account is 14 years. So our first question is, by what factor does it grow in 28 years? And our answer, we want to report in exponential notation. So I have the little formula for the growth factor right there. So it's base 2, and then our power here is going to be the amount of time that passes divided by the doubling time. Well, the doubling time is 14 years. That's the denominator of that fractional power. And then we want to know, over a period of 28 years, how much does it grow? So that's going to be the numerator. That's our t value. So if it asks for your answer in exponential notation, you want to leave that base as part of your answer. You're going to type in a 2, and then you're going to push the little power button and put in a power. And so we just want to think about, what is this power? So maybe you know that one in your head. If you do, great. If not, just see what that power is. You could do it either with the fraction button or with the division button, and you'll get the same answer. So our answer that we would type into MyMathLab is 2 squared. And again, you want it to be in exponential notation for this one. So just be really careful to read about the type of input MyMathLab wants, because sometimes, if you typed in 4 for this, it would mark it wrong because it wants it in exponential form. Okay, so for the next one, I do want you to round to the nearest hundredth. We're going to kind of switch back and forth so that you're used to hopefully just watching for what MyMathLab asks for. So by what factor does it grow in 30 years? Well, that would be 2 to the power of 30 divided by 14. And in this one, because we are getting a decimal answer, I can just go ahead and type that in. I like to use the division button for my powers. but you can use the fraction button. So it would be 4 oops, for nearest hundredth, we would round that to 4.42. So that's growing by a factor of 4.42. If you had typed it in with a fraction as your exponent, you would get exactly that same answer if you prefer a fraction like this. Okay, so then by what factor does it grow in 70 years? So again, 2 is our base. In this case, our number of years passing is 70, and we'll divide it by the doubling time, 14. This one does ask for it in exponential notation. So in my calculator, I'm not going to put the base 2. The base 2 is going to be part of my answer in MyMathLab. So I'm only going to ask my calculator to help me simplify that power. So our power is the 5th power. And that would be our answer, 2 to the 5th power. So if it says by what factor does it grow, you're just doing 2 with the power of time divided by doubling time. This next one is using our equation for the new value, which I have there on your screen. So we know our starting amount was 1,300. That's the initial value. So the new amount in the bank account is going to be that $1,300 multiplied by 2 to the power of, let's see, sorry, where's my time? 50 years divided by the doubling time, which is 14. So in my calculator, I can type that out. Initial amount multiplied by our growth factor, 2 to the power 50 over 14. Okay, so our account, if it started out with $1,300 at the end of a 50-year time period, it would have grown to $15,454.34. Okay. Next example, just a reminder as we do this example, you have to be very careful with your time units, especially when you do number 5, 7, and 11. Those ones have times that are in different terms. So like this one, we have 12 hours for our doubling time, but we have 3 days as our time period. So those are not in the same units. So we need to get them into the same units before we apply them into our equation. So in this case, 3 days, I'm going to convert into hours. Well, 3 days, well, each day is 24 hours. And so if we multiply those 3 days by 24 hours, we get 72 hours. Fun fact, I just realized that when I was writing out the notes, I said each day is 12 hours. So I need to go fix the written notes on my website. Fun times. Okay, so we know our time period that we're talking about is 72 hours now. So this one is asking us how many. So we are going to use our equation where we take that initial amount and we multiply it by our growth factor of 2 to the time over doubling time. So our initial amount is that we have 30 flies to start out. And we are going to multiply that 30 flies by 2 to the power of 72 over, and our doubling time is the 12 hours. So let's calculate that in our calculator. 30 multiplied by 2 to the power of 72 over 12. And that gives us a new population of 1,920 flies. Oftentimes, if it is like flies or people or animals, oftentimes my math lab will have you round to the nearest whole number. So even if you had gotten a decimal there, you'd probably want to round that to a whole number. Okay, if I were you, I would pause the video and go back and do numbers 1, 2, 5, 6, 7, and 8. And then once you have those ones done, you can come back to the video and we'll start with example 4, which I'm going to start right now. So example 4, at the beginning of an ecological study, a community of prairie dogs, it's supposed to be prairie dogs. They're animals. And I left part of the word out. Anyways, they have a population of 203. Researchers determined that the population is increasing at a rate of 9% per month. Make a table that shows the population for the next, as it's growing over the next 15 months. And then based on that table, find the doubling time. So to start out, month 0, our initial population is 203. So put whatever your initial population is in that first box. And then our growth rate is 9%. So that means each month we have still 100% of our prairie dogs. I mean, I guess we're kind of assuming that none of the prairie dogs die, but then plus an additional 9% being added to our population. So that's 109%, which in decimal form is 1.09, and we're going to multiply by that over and over again. So at month 1, it's 203 multiplied by 1.09. And in my calculator, I can get that value, 221.27. Now we're talking about prairie dogs, so I'm going to round to the nearest whole number there, 221. But for my next calculation, I am not going to use a rounded number. I'm going to continue using that 221.7. So for month 2 in your calculator, type in answer times by 1.09. So I'm just going to hit times and it'll use the prior answer, and then times by 1.09 to get our next month. So month 2 is 241.1843. Again, I'm going to round that for my table to the nearest whole number. And then if you have your calculator set up like this, it's pretty easy to get the next, 13 months or so, because you don't have to type anything, you just can hit enter, and it's just going to keep taking that prior answer and multiplying it. So on the 3rd month, it's going to be 263, and then hit enter again. So for the 4th month, 287. For the 5th month, 312, and then just keep on keeping on. Just be careful with your rounding. Follow just the normal rounding rules. There's one that I have to round up. And you'll be typing these into my math lab, so you will just hopefully have your calculator and just be able to input these pretty quickly. It's kind of a pain because there's so many, but it could be worse. It could be sections 5B, 15 parts that are not fun. I can't talk and write at the same time. Okay, sorry. Whoops, oh, I guess that's okay. 678 and 739. Okay, so then one last follow-up question is, based on our table, find the doubling time. And this is not like some fancy math calculation. We just need to think a little bit logically for a second. We started with 203. So double that would be 406, and we just need to figure out where on our table 406 fits in. And it looks like to me it's fitting in between the 8th and the 9th month. So the doubling time is between 8 and 9 months. And you'll just type in two numbers there into MyMathLab, and it does want you to do it in ascending order, so don't do it reversed. Okay, example 3. Okay, so we'll do example 3. Sometimes we don't know the doubling time, so we have a formula here that we can use to approximate the doubling time if we know the growth rate as a percentage. So if it's growing exponentially at p% per time period, then the doubling time is just 70 divided by p, approximately. Now that approximation works really great. It's pretty accurate for small growth rates, but anytime it starts to get over about 1500%, it doesn't work. So I think on some of the multiple choice problems, it'll have you kind of select which one this wouldn't be appropriate for. Well, anything that has a growth rate over 15%, this would not be an appropriate formula to use. Now, 99% of the time when we are using percentages in math, we want to use the decimal form. This is like the only time I can ever think of where you don't use the decimal form. If it's a growth rate of 7%, you use the 7. You don't use 0.07. So pro tip, be careful with that. So the last example that I did and the example I'm going to do next, those are what should help you get through number 3, 9, 10, and 11. So watch this next example and then pause the video and go answer those questions on your homework. So example 3, inflation is causing prices to rise at a rate of 2.5% per year based on economic data from the past year. Our first question is, what is that doubling time? So our formula is 70 divided by p. So in this case, that will be 70 divided by 2.5. So our approximate doubling time is about 28 years. So next it says, by what factor will the inflation grow in 10 years? So we're using our growth factor equation. So it's going to be 2 to the power of 10 divided by that doubling time that we just calculated, 28. And in this case, it does ask us to round, so 2, we can type it right in, 10 divided by 28. And our answer is 1.28. And we are rounding to the nearest hundredth. Please note, it is a complete coincidence that those are both 28s. It's not always like that or anything, so don't think it is. It is just a coincidence. Okay, so go back and do homework problems 3, 9, 10, and 11, and then come back and finish the video. Okay, so now we're going to switch to exponential decay and half-life. So much of this is the same, it's just we're changing the base to 1/2 instead of doubling with a base of 2, we're doing half-life, so it's a base of 1/2. So exponential decay occurs whenever a quantity decreases by that same fixed percent every time period. So instead of calling it doubling time, we call it a half-life for that time period that would repeatedly decrease to half its value. So the time required, we use half as our little subscript, and it's called half-life. After t time, an exponentially decaying quantity decreases in size to a fraction of 1/2 to the t divided by half-life. And so you'll see the word fraction show up. That doesn't always mean that your answer is going to be a fraction. This is more just like a vocabulary descriptor, like saying, oh, we only have half of the whatever you're talking about. We only have half of that, or we only have a fourth of that, or we only have 0.79 of that. So anyway, it won't always be a fraction answer. It's just the word fraction here. Our new value equation is almost identical. We're just using instead of that doubling time with a base of 2, we're using our fraction equation. Again, be careful with time units. If half-life is given in months, you've got to use months for all of the time. So I'm going to do a couple examples, and then you can go and try number 4, 12, 13, 14, and 15. Okay, so the half-life of a radioactive substance is 300 years. What fraction of the original amount will remain in 120 years? So 120 years is our given amount of time, and our half-life is up here at the top. Wow, good handwriting. Okay, so our base now is half because we're decaying, and then our given amount of time, 120, goes in the numerator, and the half-life is the denominator. On this one, we want to get our answer as a rounded decimal amount, so we will do, you can do it in the calculator several ways. If we typed it in just as the equation is shown on the paper, it's a lot of buttons. So I'm going to show you a little calculator shortcut. So we get 0.76 if we're rounding to the nearest hundredth. When I'm doing half-life and inputting into my calculator, I almost always just use 0.5 instead of 1/2 because I would so much rather type 0.5 than put in the fraction 1/2. So if you do 0.5, you can just hit that caret button and type in your power without worrying about parentheses or anything, and you'll still get the right answer. So it's a little bit easier to input in your calculator. Okay, so what fraction of the original amount will remain in 2,500 years? I can read numbers. So we've got 1/2 raised to the power of 2,500 divided by the half-life. So I'm going to do that 0.5 thing, 2,500 years divided by 300. So we get 0.003. It says rounded to the nearest hundredth, which would mean 0. So sorry, awkward. If we rounded to the nearest thousandth, it would be 0.003. Watch my math lab. It may ask you for thousandths. In fact, I think we're going to do one that it does ask for 3 decimals. So just watch for that. Okay, last one of these, and then we'll do a new value one. What fraction of the original amount will remain in 3,000 years? Now, in this case, and sometimes my math lab is going to say simplify your answer. And in that case, it does not want a rounded answer. It wants a fraction answer. So I need to show you how to get that. In this case, we will, kind of write it out same as we have been. The base is 1/2. Our time period is 3,000 years, and we're going to divide that by the half-life. But instead of typing it in our calculator, because if we do, no matter what we get, or no matter what buttons we push, we are going to get a decimal answer, and the calculator usually won't convert it into a fraction. So we have got to do the work here. What you can do in your calculator is just figure out the power. Maybe you can even just do that in your head. So the power here, whoops, I missed a 0. The power here is 10. So calculate the power. It won't always be one that you can easily do in your head, but that one you probably could have. So that's 1/2 to the 10th power. Well, there's a fraction power rule that looks like this. If you have a fraction raised to a power, you can just do the power individually to the numerator and denominator. So we could separate this as a 1 to the 10th over 2 to the 10th. 1 to the 10th is just 1. And then 2 to the 10th we can ask our calculator for. Now I'm not putting the fraction in. I am just literally asking the calculator to help me with the denominator. So the denominator is going to be 1024. And then I would type that fraction into my math lab as your answer. Okay, and that's that fraction answer you need to do when it says simplify. If it's not telling you how to round it, it means you need to put it in as a fraction. Okay, so if you started with 650 kilograms, how much would remain after 500 years? So it's going to be that initial amount multiplied by 1/2. Our time period in question is 500 years, and we're going to divide that by the half-life, which is 300. And we can punch that into our calculator. And you can, again, use 0.5 instead of 1/2 here, and it'll work just fine. Okay, so after 500 years, we would have 204.74 kilograms. Okay, you can go do those other homework questions if you want, and then there's just one last section if you want to just watch the rest of the video, that's fine too. Okay, so this is the approximate half-life formula. We did the approximate doubling time formula before. It turns out the formula is the same. Thank goodness. I hate it when there's a million different rules. But that same formula works here. We just take the number 70 and divide it by in this case, decay rate. So again, this works best for small rates of decay. If it's decaying at a rate faster than 15%, then this formula does not do well, and there's a different formula you'd have to use. So I'm going to do a couple examples here, and then you can finish up the rest of that homework assignment. So example 6. A clean-up project is reducing the concentration of a pollutant in the water supply, and they're able to get a 3.5% decrease per week. What is the approximate half-life? And then based on that half-life, what fraction of the original amount will remain after 1 year? So first of all, before we get too far into this, our time periods do not match. Our rate is given to us as a per week number, and our question is about 1 year. So we're going to convert that 1 year into weeks. And if you didn't know, 1 year is 52 weeks. So we're going to use that 52 weeks in place of 1 year when we get to that problem. Okay, so what is the half-life? Well, we just take 70 and we divide it by 3.5. That's 20 weeks. So now that we know the half-life, we can figure out what fraction is remaining. So what fraction is, when we're going to just use that base of 1/2, and we are going to take our given time period, 52 weeks, and divide it by the half-life, which we just calculated, 20 weeks. We're going to use that down here. Okay, so let's crunch that. Half raised to the power of 52 divided by 20. So we get that there will be about 0.165 if we round to the nearest thousandth, so 3 decimals there. So between, so that would be like 16%, 17% of the pollution left. Okay, I think that's actually it. That's it. So that's the video for 8.3. Let me know if you have questions. Thank you.